This is my first video on special theory of relativity. So the title is When Does Classical Mechanics Fail, or Why We Need Special Theory of Relativity. So let us first define the frame of reference. So if you have a suitable axis system and plus length and time scale, so you call it a frame of reference. For example, this is my axis system, so I can define a suitable length scale and a suitable time scale. So if I have length scale and time scale, so I can define a position vector and I can find the velocity, so from where I can get the momentum, and all other physical parameters can be measured. So frame of reference contain axis system plus suitable length and time scales. Next is the motion is relative. So this is an important concept to remember. You know how we define motion. So if there is a velocity or there is, so we say there is a motion. So let's say this is my frame. So at a particular time the position vector for a particular physical system is r, and after some time t this position vector changes. So we can use the calculus to find this derivative. So this derivative is basically velocity. So if velocity is 0, means our system is at rest, and if that velocity is not equal to 0, so obviously there is a motion. But look here, if a bus is moving on a road with a constant velocity v in a particular direction, and here we have an observer which is standing on the bus stop. So we can define a frame of reference here. So this is our axis system and we have some suitable length and time scale. So at time t is equal to 0, let's say this person forms a position vector of a particular point on this point, and this is r. And obviously, since we said that the bus is moving, so after some time t this bus will be somewhere here. So we can define other position vector and from there we can find velocity. So obviously this bus is in motion with respect to this observer. But if we define our frame of reference on the bus, let's say there is a passenger within the bus, and now this is our frame of reference. So according to this observer, at a particular time, this observer which was standing on the bus stop, so he can define a position vector here. And since according to this frame the bus is moving, but now this will appear that this particular observer which is standing on the bus stop is moving in this direction, means after some time its position vector will be somewhere here. So this particular observer in this frame, in this S prime frame, will observe that the observer which is standing on the bus stop is moving backward with some speed, with the same speed but in opposite direction. So now what we can say, that which either the bus is moving or the observer is moving. So which one is true? So the idea is that both are true. So the motion is relative, it is not absolute. So we cannot say that this object is in motion. So all we have to do is to define frame of reference. So one particular physical object may be in motion in one frame and it may be at rest in some other frame. So motion is relative. So now if there is a relative motion between two observers, so they measure some physical quantities, they perform some experiment. So obviously the physical quantities should be same. So for example, if there is a observer which is moving in a car in a particular direction and another observer which is at rest, and here is some physical phenomena, maybe there is a aeroplane is moving. So if this observer measures this speed of this aeroplane and this measures the speed of aeroplane, so both should be equal. This is what our classical mechanics tell us. So relativity, so this is basically relativity. So there is a relative motion and this observer are measuring the same experiment. So if we know the value of our experiment or the physical quantities in this frame, so we can shift to this frame, so we can know that what are the values in this. So this is relativity and this is described by classical mechanics. So if the relativity is described by classical mechanics, then why we need another theory for relativity, which is usually known as the special theory of relativity. So the idea is that there are certain physical phenomena which cannot be explained on the classical mechanics, on the basis of classical mechanics. So this is somehow we are discussing the history. So the first is troubles about time. So a pion is a subatomic particle and its lifetime is 26 nanosecond, means when this pion is created, so after this time 26 nanosecond this decays into some other particles, so it has lifetime of 26 nanosecond. But it was observed that if this pion is created with this speed which is almost compared to the speed of light, which is 91% of speed of light, so the lifetime of this pion increases and it becomes 63.7 nanosecond. So there is a simple experiment when the, let's say, pion was created here in motion, and when it will decay, so it will decay at here. So if we measure this distance, so this distance experimentally it was measured to be 17.4 meter. So this is our distance. We know the speed v, so using the simple relation s is equal to vt, we can find the time. So time is basically s by v or d by v. So this is experimental value, this is experimental value. So the time lifetime is 63.7 nanosecond, which is almost 2.5 times larger. So what is this? According to classical mechanics, time is an absolute quantity, but here in two different frames, in one frame it is at rest, so it gives us this time, and another frame it is in motion, so it gives us this lifetime. So according to classical mechanics, time is an absolute quantity, but here we see that time is not absolute. Just like motion, time is also relative. So we will see that how this problem is resolved. So the next is troubles with length. So we discussed the creation of pion. So look here, let's say this our S frame and this is x is equal to 0, and the pion is created here and it is in motion, so it decays somewhere here. So the distance traveled is 17.4 meter. So if we have an observer in this frame, the frame in which the pion is in motion, so he will measure this distance as 17.4 meter. Obviously it was done, but also we know that when the pion is created at rest, so it has 26 nanosecond lifetime. So if we have a frame, let's say here I am this picture, so if this frame is also moving with this speed, with the same speed as the pion is moving, so pion will appear at rest. So if pion is at rest in this particular frame, so it has a lifetime of 26 nanosecond. So from this frame it will appear that this observer S is moving in opposite direction, because we discussed that the motion is relative with the same speed v. So if this is moving in opposite direction, so let's say when the pion was created in S prime frame, so at that time we marked this this point here, and after when this pion decays, so this particular point on this S frame has moved here, so we can measure this distance. So how can we measure? We know the time period, we know the speed of motion of this particular point in S frame, so we know the speed, we know the time, so this gives me 7.1 meter. So this is another problem. So one observer measures the length to be 17.5 meter, the distance traveled to be 17.4 meter, and the other observer measure the same distance to be 7.1 meter. So that is another problem, means the length is also relative, the distance traveled is also relative, it has something to do with the motion. The next is the troubles with speed. So let's take a very simple example. So it is basically an hypothetical experiment or mental thought experiment. So let's say here in person A, and here is another person B, and here an observer O. So this A throws a ball with speed v, which is greater than speed of light, and this person catches that ball. So you know that how we see object. So we see the object when light from that particular phenomena reaches us. So that is our observer. So when this person throws ball, so the light travels with speed c. So ball reaches first and the light reaches after that. So it means that the light signal that are carrying the information about this particular phenomena will reach here later than here. So ball reaches here and this person catches this ball, so also the light signal carrying that particular information travels in this direction to our observer O. So this signal from B reaches first and the signal from A reach later. So to this observer it will appear that the ball is being catched first and thrown later. So this is the violation of cause and effect. So cause is always before then the effect. So first there is a cause and then there is effect. For example, so if an apple drops from the tree and falls on the ground, so dropping of an apple is the cause and falling is the effect. So you cannot find a frame in which it will appear that the apple is on the ground first and then it falls from the tree. So this is a violation of cause and effect. So classical mechanics does not put a limit on the speed. So we may have this speed which is greater than speed of light. So this is another problem. So if objects can move with greater speed of light, so there is a violation of cause and effect. This is also known as the principle of causality. The next problem was the troubles with energy. So here take an example. Let's say here we have an isolated system. Isolated system, so no force is being exerted on this system from outside, no heat exchange and all this. And here we have two particles, electron and positron. So electron and positron are antiparticle to each other. So when they combine with each other, so this reaction happens. So electron plus positron gives us two gamma rays. So these two gamma photons are emitted in opposite direction and they will be absorbed by the wall of these containers. So the energy of the container, the wall of container will increase. So there is a change of energy. Although the system is isolated, so there should not be any change in the energy. So this is a violation of conservation of energy. So if this reaction happens, so there is a violation of the idea of classical conservation of energy. So it means that we need to redefine the energy. And also you see here the mass is destroyed, which is against the conservation of mass. So that was problem with the energy. And there is another problem that was with light. So you know that light is an electromagnetic radiation in which we have electric field E and magnetic field B. So this electric field is oscillating. So this oscillating electric field produces this magnetic field B, and this oscillating magnetic field will produce this E. So if a person moves with light, let's say this is a particular point on light, let's say our observer is here and it is also moving with speed c. Light is also, this particular portion is also moving with speed c. So to this observer, this electric field will appear as static electric field because this is moving at the same speed. So there should be static electric field. So if there is a static electric field, so there should be a static magnetic field. Mean if the electric field is not oscillating, it is not changing with respect to time, so there should not be any magnetic field. So if there is static electric and magnetic field, so we cannot have light, we cannot have electromagnetic radiation. So that was another problem. So to an observer moving with speed of light, there is static electric field. So the entire electromagnetism, the electromagnetic theory for light fails. So these were few troubles with our classical idea. So these types of phenomena could not be explained on the basis of classical theory. So therefore it was required to have a new theory that could explain these particular phenomena. So that is also, next video I will talk about the Galilean transformations.